So let's dive into now our problem statement. So the goal here, every time an object comes within 10 centimeters of our robot, the robot moves in the opposite direction of its last movement. The first time the sensor is tripped, the robot should move forward. If nothing is in front of the robot, then it'll stop. And the robot will stop when the touch sensor is pressed. So think about that for a moment. It's pretty easy to see how the structures and the functions that we've just looked at are going to come into play here. Let's take a little more detailed look at a flowchart of this problem. So if we start off at the center point here, first thing we're going to do is check our sonar distance. If a target is found, we're going to check our Boolean status. So we're deciding that we're going to use a Boolean value to remember what direction we're moving. So if the Boolean status is true, we're going to move forward, wait, and then flip the Boolean value. If the Boolean value is false, we're going to move backwards, wait, and then flip it to true. After we've done that move, we're going to check the touch sensor status, and if it was pressed, stop everything. And if it wasn't pressed, go back around to checking our sonar distance. And then if no target was found when we check that, then we're going to stop our motors and wait half a second. So now that we've thought about this, we've seen some structures, we've seen the not function, we've seen the select function, we've seen the shift register capability of while loops. Let's go ahead and program this up for our autonomous code. So I'll step back into LabVIEW, open up my autonomous mode, which, because this is just a default template, is completely empty right now. And let's get started. Probably the best way to begin is to check our ultrasonic distance. That's the first thing that needs to be done. So if we go to our NXT.io palette, choose our sensor palette, place it down, use the use the polymorphic VI selector to choose our read ultrasonic. We need to specify our port, so we're going to right-click, create constant to choose port 2, because that's the default port that we're going to use in this case for our ultrasonic sensor. And the first comparison we need to do is check whether something is close, whether something is less than 10 centimeters away. So to get that comparison done, we need to go again into our programming palette, comparison subpalette, throw our less down. It's auto-wired there, but put the wrong terminal in, so I'm going to delete that. Bring up our context help, which is always convenient. Remember that shortcut, Control-H. Wire our distance out of the sonar into the top terminal here, and then create a constant of 10. So the first thing we've done here is we've now performed that initial piece of the flowchart, which is to check our sonar distance. We know we want to do one thing if the target is not found and another thing if the target is found. So the second piece of the puzzle is a case structure. We get that from our structures palette, put down a case structure, and wire the selection terminal to the result of our comparison. So it never hurts to document as you go. It's a great hint that you can double-click anywhere in our block diagram to bring up a free label. And here we can say check sonar distance, clean up our typos, and inside here, if we're in the true case, we can say object detected. So if an object was detected, what we want to do is we want to make our DC motors go. We want to drive. So we go ahead into our Tetrix subpalette, to our DC move motors, place that guy down. The next thing we always do after we place a motors function for the first time is specify using a constant which motors we want to drive. We're going to actually drive both of them, so we're going to choose left wheel, triangle to expand, and then right wheel. And we saw this hint in an earlier webinar. Because we're going to be calling this same motor configuration in multiple places, it's simpler and cleaner to actually pull it outside of our structure and just call it inside. So the next thing we should do, just to keep everything clean, we should be taking advantage of our NXT terminals. And now we've got some decisions to make here. If we go back to our flowchart, we need to decide whether or not we're moving forwards or backwards based on our target found status. Sorry, we need to, now that we've found, we know we're in that we've found our target, we need to decide whether to move forwards or backwards. So let's put in, now we want to be able to implement this using a shift register. So let's go ahead and expand our internal structure here to make a little bit more room. Just go ahead to our structures palette and place a while loop around all of our code. And as they say, there's always many ways to skin a cat. There's many ways to generate LabVIEW code, and there's many orders in which you can do things. There's not necessarily a right or a wrong order. I know for myself, I like to start on the inside and work out. Some people, it would be very natural to start with the while loop. But in this case, as long as everything gets placed before the end of the program, everything will be fine. So we've got our while loop now because our behavior is going to run over and over again. And the next thing we need is to add our shift register. So we're going to right-click somewhere on the edge, add our shift register. In this case, we want it to be a Boolean. And we know also, something from the problem description, that the first time it goes, we want the value of that Boolean to be true. So let's go to our NXT programming subpalette, into our Boolean subpalette, and take a true constant to initialize that shift register. So by wiring that in, we saw the initialization behavior when we were playing with the iteration terminal in the previous example. That'll make sure that the first time through this loop, this value is true. So what do we need to do with this value? Well, this value is being used to decide whether we're moving forwards or backwards. So let's say if it's forwards, if the value is true, we want to go a speed of 50. So let's create a constant for our speed of 50. We actually don't want that directly connected. This is where we're going to take advantage of that select function. So we're going to go to our NXT programming subpalette, again into the comparison subpalette, and here is that select function we were looking at a moment ago. By placing this guy down and wiring the select to the value in our shift register, we're going to be able to choose between our 50, and if we make a control drag to duplicate this guy, a minus 50. So now we've got a speed that's being selected based on the value in the shift register. And because it's going from a positive to a negative number, we're going to flip directions, which is exactly what we need to do. This value then goes into the speed terminals of the move DC motors function. And we need to also add a delay. So we're going to put a half-second delay here using the NXT terminals, as we've learned in previous webinars, to make sure our sequence is enforced. And the last piece of the puzzle for the true case here, if we return to our flowchart, is we need to move, wait, and then flip the Boolean value. So that, as we saw before, from the Boolean subpalette, we take advantage of the not function. So we can make a little bit more room to make sure our code is nice and clean. We're going to wire up the value coming from the shift register and take the inverted value back into the right-hand side. So we've achieved here everything that we need to for the true case. So let's take a closer look at our flowchart for the false case. If the target is not found, what we want to do is stop the motors and have a short delay. So we flip over to our false case, we go into our Tetrix palette, DC motors stop. We see the benefit of having wired our motor constants from the outside, because that wire is just sitting there waiting to be used. We connect up our NXT terminal from the left-hand side, and again we put a short delay in. So again from the NXT.io palette, the wait function, wire up the NXT terminal for sequencing, create a 0.5 constant to define the time delay, and output the NXT sequence. Output the NXT terminal to the right-hand side. So you may notice something important here. When we talked about case structures in previous webinars, we talked about how important it was to wire all the values through. And we see that we have an open tunnel here. We have an open square on the output side. This is important in reminding us that we must wire a value through it. And if the value was false, what we're going to do is just take the value from the shift register straight on through. And this is one of the really nice uses of shift registers, because you can have the behavior of flipping be dependent on sensor behavior. So if nothing is detected, we're not going to change directions. And we ensure that by wiring right on through the shift register. So we're almost done. The last piece of the puzzle, if we return to our flowchart to take a quick look, is to check the touch sensor status and then either continue the code or stop the code. Again, we've got all the pieces we need here. In fact, our program is broken right now, and the reason why is that the conditional terminal of the while loop hasn't been wired. So all we need to do is from our NXT.io palette, pick up another sensor block, choose the read touch sensor, pressed, use the NXT terminal for sequencing, and right-click to choose our port. In this case, we're going to choose port 4, which is the default configuration for the robot as we've got it. And all we've got to do is take this resulting value into the end condition of our while loop. So with a handful of blocks, and even while talking, about 10 minutes worth of programming, we've achieved an interesting and somewhat sophisticated behavior by using LabVIEW. And there's one other option you could do, and it's not bad practice, for when the code is completed, to take another copy of the break function and take it outside the while loop, get our context help out of the way, use the NXT terminal to sequence this, and just connect again to the same motor constant so that if we do press our touch sensor, not only does the program stop, but we're taking control of the movement of the robot and stopping it ourselves. So in summary, we've covered 3 important new functions within LabVIEW. One is the shift register contained in while loops. One is the not function. And third is the select function. And we've used this as a stepping stone into some significantly more sophisticated programming techniques, which we're going to get into in the next webinar and the one after that, where we're going to actually use this as a starting point for implementing a state machine, which is a very exciting and tremendously flexible structure that will really allow you to create code, especially autonomous code, that can perform all kinds of interesting behaviors. So at this time, we'll stop for any questions that you may have. We've got a question. So the question is how to display the joystick Y and X axis on the screen of the brick during competition. That's a really interesting question. Clearly that's for the teleop portion and not the autonomous portion, because it doesn't make sense to ask what the joystick status is during autonomous. So let's, why don't we take a quick peek then? That's a great question. Let's take a quick peek into some sample teleop code. So I'm going to go ahead and save and close my autonomous code. We're going to open up the default remote control configuration, and we're going to use it, like we did in the previous webinar, to actually generate our teleop code. So let's do that. Generate code. And this is, you can watch this offline, so this is our teleop code. If you didn't see the previous webinar, you can find it on tetrixrobotics.com/FTC, where we go into a lot of detail about how to actually generate and modify this teleop code. So the first part of the question is, how do I get the joystick values? Well, we have palettes here which are returning button ID, palette functions, and here we've got the left and right motor power coming out of the tank function. That's not exactly what you're asking for. But if we were to open up this function, which is an interesting thing that we can always do, you see that when we look at the code and the front panel, that there's a variety of parameters available. Now, I'm not going to go into a ton of detail as to exactly how to what all of this means, but essentially what we have here is a bundle of information called the controller state that's being put into an unbundle function. and where you can see the left and right y-axes are being pulled out. Well, if we wanted to modify this, let's actually not modify it here. Let's make a modification outside in our main part of our teleop code. There's a great shortcut when you need to make more space, and I think I've mentioned it in a previous webinar. If you press the Control key while dragging, you get to grow your block diagram. So what we have here on this brown wire is actually a collection of all the joystick information that's been received from the field controller system. So if I right-click our NXT programming palette and then cluster subpalette, something called unbundle by name, which I can place down. What the unbundle by name guy lets us do is wire in a cluster of information, and then by clicking and expanding it, and then by clicking in the blocks, choosing which information to extract out of there. So let's say you want the left X and the left Y. You've got these two numbers here now. So the next thing you can do is there's a whole bunch of functions that are available to write to the NXT display. And we talked about those in a previous webinar as well. So if we can find those in NXT.io and then the display function. So here you've got some choices as to what you want to write to it: text, integer, or float. In this case, we've got two integers that we want to write. So we can use this function actually twice. Once for left X, Control drag to make another one. Once for left Y. And then what we have to do is specify which line to display it on. So on this top input, you see there's an input called line. We can create a constant, right-click, create constant. We can do line 1, and then the second one, right-click, create constant, and do line 2. So there's a simple, quick, and dirty way to show the joystick values on the brick display. You can get a lot fancier by using, instead of writing the int, you could write text string, and you could format and say things like left joystick value is colon, and then right joystick value is colon. But either way will do, and you can just get as creative as you need to be. Great. Thank you very much for your time. We appreciate you all joining us. And please register again for the webinar that will be next week. Thanks, and have a great evening.